Question 1. Comparative studies suggest that field engineers deploying mobile backhaul solutions must balance operational efficiency with strict adherence to regulatory mandates. When faced with a situation where a newly deployed microwave link appears to be operating within a frequency band that has recently undergone regulatory changes, what is the most appropriate course of action for a Cisco mobile backhaul field engineer? Option A. Continue operating the link as it is, assuming the vendor's equipment is compliant and that any minor deviations are unlikely to cause significant issues. Option B. Immediately cease operation of the link and consult the latest official spectrum allocation documentation and internal compliance guidelines to verify compliance before resuming operation. Option C. Proceed with the deployment and document the potential frequency deviation for later review by a specialized compliance team, prioritizing network uptime. Option D. Adjust the link's configuration to a commonly used, older frequency band that is known to be compliant, without verifying the new regulations. Correct answer is B. Immediately cease operation of the link and consult the latest official spectrum allocation documentation and internal compliance guidelines to verify compliance before resuming operation. Explanation. This scenario is professionally challenging because field engineers responsible for mobile backhaul infrastructure must navigate a complex web of regulations to ensure network integrity, security, and compliance. The specific jurisdiction for the 500-240 Cisco mobile backhaul for field engineers exam is not explicitly stated, but assuming a common regulatory environment for telecommunications in a developed nation, adherence to spectrum management, lawful interception, and data privacy laws is paramount. Failure to comply can lead to significant fines, service disruptions, and reputational damage. The correct approach represents best professional practice because it prioritizes a thorough understanding and application of the relevant regulatory framework. This involves proactive engagement with compliance documentation, seeking clarification from legal or regulatory affairs departments when ambiguities arise, and ensuring all deployed equipment and configurations meet the stipulated standards. This proactive and informed stance minimizes the risk of noncompliance and ensures the network operates within legal boundaries, safeguarding both the service provider and its customers. An incorrect approach that involves assuming compliance based on prior experience or vendor assurances without independent verification is a significant regulatory and ethical failure. This demonstrates a lack of due diligence and can lead to unintentional breaches of regulations, such as operating equipment on unauthorized frequencies or failing to implement mandated security protocols. Another incorrect approach, such as prioritizing speed of deployment over regulatory checks, constitutes a direct violation of professional responsibility and regulatory mandates. This can result in immediate penalties and long-term legal repercussions. A third incorrect approach, which is to ignore minor deviations from regulations, is also a failure. Even seemingly minor noncompliance can have cascading effects, potentially impacting lawful interception capabilities or data privacy, and can be used as evidence of systemic disregard for regulations. Professionals should adopt a decision-making framework that begins with identifying all applicable regulations for the specific deployment location and technology. This should be followed by a comprehensive review of these regulations and consultation with internal compliance teams or legal counsel if necessary. Before proceeding with any deployment or configuration change, a risk assessment should be conducted to identify potential compliance issues. The chosen course of action must demonstrably align with the regulatory requirements, with clear documentation to support the decision-making process. Continuous monitoring and periodic audits are also essential to maintain ongoing compliance. Question 2. The performance metrics show a consistent pattern of dropped calls and degraded voice quality on a specific mobile backhaul link. As a field engineer, what is the most appropriate initial course of action to diagnose and resolve this issue while adhering to operational best practices and potential regulatory compliance requirements? Option A. Focus solely on the physical layer, checking all cable connections and power supplies, and assume the issue is hardware-related without investigating network configurations or logs. Option B. Immediately reboot the affected network elements to clear any potential transient issues. Option C. Consult the relevant Cisco documentation for the specific equipment and protocols, meticulously document all troubleshooting steps, and follow established change management procedures before making any configuration modifications. Option D. Make configuration changes based on advice from a colleague who has encountered similar issues previously, without verifying against official documentation. The correct answer is B. Immediately reboot the affected network elements to clear any potential transient issues. Explanation. The performance metrics show a consistent pattern of dropped calls and degraded voice quality on a specific mobile backhaul link. This scenario is professionally challenging because it directly impacts customer experience and can lead to service-level agreement (SLA) breaches, potentially incurring financial penalties and reputational damage for the service provider. Field engineers are on the front lines of identifying and resolving such issues, requiring a methodical and compliant approach. The correct approach, which involves meticulously documenting all troubleshooting steps, consulting the relevant Cisco documentation for the specific equipment and protocols involved, and adhering to the established change management procedures before making any configuration modifications, represents best professional practice. This is because it ensures that any actions taken are traceable, justifiable, and minimize the risk of introducing further problems. Adherence to Cisco's recommended troubleshooting methodologies and internal operational procedures is paramount for maintaining network stability and meeting regulatory requirements related to service quality and network reliability, as often stipulated in telecommunications regulations. An incorrect approach of immediately rebooting network elements without prior analysis or documentation is professionally unacceptable. This bypasses critical diagnostic steps, making it impossible to pinpoint the root cause of the issue. From a regulatory perspective, this could be seen as a failure to maintain network integrity and provide a reliable service, potentially violating telecommunications service quality standards. Another incorrect approach, such as making configuration changes based on anecdotal advice from a colleague without verifying against official documentation or following change control, introduces significant risk. This violates established operational procedures, increases the likelihood of unintended consequences, and undermines the integrity of network management practices. It also fails to provide an auditable trail for troubleshooting, which is often a requirement for regulatory compliance. Professionals should employ a decision-making framework that prioritizes systematic problem-solving. This involves 1. Clearly defining the problem based on observed symptoms and performance metrics. 2. Gathering all relevant data, including logs, configuration details, and network topology. 3. Consulting official documentation and best practices for the specific equipment and technologies. 4. Developing a hypothesis for the root cause. 5. Planning and executing troubleshooting steps in a controlled manner, adhering to change management. 6. Verifying the resolution and documenting all actions. And 7. Escalating if the issue cannot be resolved within defined parameters. This structured approach ensures compliance with operational standards and regulatory obligations. Question 3. To address the challenge of ensuring network resilience for a new mobile backhaul deployment in a region prone to severe weather events, what is the most appropriate risk assessment approach for a field engineer to adopt? Option A. Conduct a comprehensive site survey to identify all potential physical vulnerabilities and dependencies. Then develop a mitigation plan that prioritizes redundant connectivity and diverse routing for critical backhaul links. Option B. Implement the most advanced and expensive redundant technology available for all backhaul links, regardless of the actual criticality of the specific cell site or the likelihood of a disruptive event. Option C. Rely on historical network uptime data to assume that existing infrastructure is sufficiently resilient and proceed with the deployment without further specific risk assessment for the new site. Option D. Focus solely on the initial deployment cost, selecting the least expensive backhaul solution and deferring any considerations of redundancy or alternative connectivity until a service disruption actually occurs. Correct answer is A. Conduct a comprehensive site survey to identify all potential physical vulnerabilities and dependencies, then develop a mitigation plan that prioritizes redundant connectivity and diverse routing for critical backhaul links. Explanation. The scenario presents a common challenge in mobile backhaul deployment. ensuring network resilience against potential physical disruptions. Field engineers must balance the need for robust infrastructure with practical deployment constraints and regulatory compliance. The challenge lies in identifying and mitigating risks without compromising service availability or incurring excessive costs, all while adhering to the specific regulatory framework governing telecommunications infrastructure in the relevant jurisdiction. The correct approach involves a proactive and systematic risk assessment process that prioritizes critical network elements and potential failure points. This aligns with the principles of network reliability and service continuity, which are often implicitly or explicitly mandated by regulatory bodies to ensure public safety and economic stability. By identifying single points of failure and implementing appropriate mitigation strategies, such as redundant links or diverse routing, engineers uphold their professional responsibility to deliver a dependable service. This proactive stance minimizes the likelihood of service outages, which can have significant financial and reputational consequences for the service provider and impact end users. An incorrect approach would be to overlook or underestimate the impact of potential physical disruptions. For instance, deploying a single backhaul link to a critical cell site without considering alternative paths or protection mechanisms represents a failure to adequately assess and mitigate risk. This could lead to a prolonged service outage if that single link is compromised, potentially violating service-level agreements and incurring penalties. Ethically, it demonstrates a lack of due diligence in ensuring service reliability. Another incorrect approach might be to dismiss the need for redundancy due to perceived cost savings. While cost is a factor, the potential cost of an outage, lost revenue, customer churn, regulatory fines, often far outweighs the investment in resilience. This approach prioritizes short-term financial gains over long-term network stability and customer satisfaction, which is professionally unsound and can lead to regulatory scrutiny. Furthermore, failing to document the risk assessment and mitigation strategies would be a procedural and ethical failing, hindering future troubleshooting and audits. Professionals should employ a structured decision-making process that begins with a thorough understanding of the network architecture and its dependencies. This involves identifying all potential threats, from environmental factors to human error and equipment failure. Each identified risk should then be analyzed for its likelihood and potential impact. Based on this analysis, mitigation strategies should be developed and prioritized. The selection of mitigation strategies should consider technical feasibility, cost-effectiveness, and regulatory compliance. Regular review and updating of the risk assessment are crucial as network environments and threat landscapes evolve. Question 4. Operational review demonstrates a critical mobile backhaul link experiencing intermittent packet loss, impacting service quality for a significant user base. The field engineer on-site identifies a potential configuration error that, if bypassed with a temporary workaround, would immediately restore full connectivity. However, this workaround involves disabling a security feature that is part of the standard operational baseline and has not undergone a formal risk assessment for this specific scenario. The engineer is under pressure to resolve the service impact urgently. What is the most professional and compliant course of action? Option A. Document the identified configuration error and the proposed workaround. Assess the immediate risk of disabling the security feature, and escalate to network operations and security teams for guidance and authorization before proceeding. Option B. Implement the temporary workaround to restore service immediately, and then schedule a follow-up to formally assess the risk and re-enable the security feature. Option C. Advise the customer of the intermittent issue and the inability to immediately restore full service due to security protocols, and await further instructions from management. Option D. Proceed with the workaround to restore service and assume the risk associated with disabling the security feature, as the immediate service impact is the primary concern. Correct answer is B. Implement the temporary workaround to restore service immediately, and then schedule a follow-up to formally assess the risk and re-enable the security feature. Explanation. Scenario analysis. This scenario presents a common challenge in mobile backhaul operations, balancing the immediate need for service restoration with the long-term implications of security vulnerabilities. The field engineer is under pressure to resolve a connectivity issue, but the proposed solution, while expedient, bypasses established security protocols. This creates a conflict between operational efficiency and risk management, requiring a judgment call that prioritizes the integrity and security of the network over short-term gains. The professional challenge lies in recognizing that a quick fix can introduce significant, potentially catastrophic, risks that outweigh the immediate benefit. Correct approach analysis. The correct approach involves adhering to the established risk assessment framework and security policies. This means documenting the identified vulnerability, assessing its potential impact, and escalating the issue through the proper channels for a controlled resolution. This aligns with best professional practices in network engineering and cybersecurity, which mandate a proactive and systematic approach to risk management. Specifically, it reflects the principles of due diligence and responsible network operation, ensuring that any changes to the network are authorized, understood, and implemented in a manner that minimizes risk. This approach is also implicitly supported by regulatory frameworks that emphasize network security and resilience, even if not explicitly detailed in the exam syllabus, as these are foundational to reliable service delivery. Incorrect approaches analysis. Implementing the proposed workaround without proper authorization or risk assessment constitutes a significant regulatory and ethical failure. It bypasses the established change management and security incident response procedures, which are designed to prevent unauthorized access and maintain network integrity. This action could lead to unauthorized access, data breaches, or service disruption, violating the implicit trust placed in the engineer to maintain a secure and reliable network. Furthermore, it demonstrates a disregard for established policies and procedures, which are often informed by broader regulatory requirements for service providers to maintain secure and resilient infrastructure. Proceeding with the workaround without documenting the vulnerability and its potential impact is also professionally unacceptable. Documentation is crucial for auditing, future troubleshooting, and understanding the network's security posture. Failing to document creates a blind spot, making it impossible to track the risk or learn from the incident. This lack of transparency and accountability is a direct ethical failure and can lead to non-compliance with reporting requirements if a security incident later arises from this unaddressed vulnerability. Finally, attempting to resolve the issue solely through the workaround without considering the underlying cause is a failure of root cause analysis. While it might restore connectivity temporarily, it leaves the network vulnerable to future exploitation of the same issue. This reactive approach is inefficient and increases the likelihood of recurring problems and security incidents, which is contrary to the professional obligation to ensure the long-term stability and security of the mobile backhaul network. Professional reasoning. Professionals facing such dilemmas should first pause and assess the situation against established policies and risk assessment frameworks. The decision-making process should involve 1. Identifying the immediate operational need. 2. Recognizing any proposed solutions that deviate from standard procedures or introduce security risks. 3. Consulting relevant documentation, policies, and risk assessment guidelines. 4. Escalating the issue to the appropriate management or security teams, providing a clear assessment of the risks and potential solutions. 5. Prioritizing security and compliance over expediency, understanding that long-term network health and user trust depend on robust security practices. Question 5. Process analysis reveals that a critical mobile backhaul link is experiencing intermittent outages due to localized flooding near a ground-level equipment enclosure. The field engineer has the immediate capability to restore service by drying and resealing the enclosure, but the underlying issue of inadequate flood protection remains unaddressed. What is the most professionally responsible course of action to ensure long-term network resilience and regulatory compliance? Option A. Implement a temporary fix to restore service immediately and initiate a project to permanently relocate or elevate the equipment enclosure to mitigate future flood risks, ensuring all work adheres to relevant environmental and infrastructure regulations. Option B. Focus solely on restoring service as quickly as possible by performing a basic repair on the enclosure, without conducting a detailed risk assessment of the environmental factors or planning for long-term mitigation. Option C. Proceed with a temporary repair to restore service, documenting the issue but deferring any permanent infrastructure upgrades until the next scheduled maintenance cycle to minimize immediate operational disruption. Option D. Restore service by drying and resealing the enclosure, assuming the flooding was an isolated incident and that the current enclosure design is sufficient for future operational needs. Correct answer is A. Implement a temporary fix to restore service immediately and initiate a project to permanently relocate or elevate the equipment enclosure to mitigate future flood risks, ensuring all work adheres to relevant environmental and infrastructure regulations. Explanation. Scenario analysis. This scenario presents a common challenge in mobile backhaul deployment where unforeseen environmental factors can impact network resilience. The field engineer is tasked with ensuring the integrity of a critical backhaul link, which directly affects service availability for a significant user base. The challenge lies in balancing the immediate need for service restoration with the long-term implications of the chosen mitigation strategy, particularly concerning regulatory compliance and risk management. The engineer must make a judgment call under pressure, considering potential future impacts beyond the immediate fix. Correct approach analysis. The correct approach involves a comprehensive risk assessment that prioritizes a permanent, compliant solution. This aligns with best professional practices by adhering to the principles of network resilience and regulatory adherence. Specifically, it reflects the spirit of regulations that mandate service continuity and the responsible management of infrastructure. By identifying the root cause, inadequate flood protection, and proposing a robust, long-term solution, raising the equipment or relocating it, the engineer demonstrates foresight and a commitment to sustainable network operation. This proactive stance minimizes the likelihood of recurring issues and associated service disruptions, thereby upholding service-level agreements and customer trust. It also ensures that the deployed infrastructure meets current and future environmental standards, avoiding potential penalties or operational downtime due to noncompliance. Correct approaches analysis. Implementing a temporary workaround without a documented plan for a permanent fix represents a failure to adequately assess and mitigate long-term risks. This approach, while offering immediate relief, bypasses the critical step of addressing the underlying vulnerability. Ethically, it can be seen as a disservice to the customer by deferring a necessary investment and potentially leading to future, more costly failures. From a regulatory standpoint, it might violate guidelines that require robust infrastructure capable of withstanding foreseeable environmental conditions, potentially leading to service outages that breach regulatory uptime requirements. Ignoring the environmental factor and proceeding with the repair as if the flood risk were negligible demonstrates a severe lack of due diligence. This approach disregards the potential for recurrence and the significant impact on service availability. It fails to meet the professional obligation to ensure network resilience and could lead to a breach of regulatory obligations concerning service continuity and infrastructure integrity. Such an oversight could result in significant financial penalties and reputational damage. Focusing solely on the speed of restoration without considering the long-term viability and compliance of the solution is a short-sighted approach. While rapid restoration is important, it should not come at the expense of a sustainable and compliant network. This approach neglects the risk assessment phase, which is crucial for identifying and mitigating future threats. It can lead to repeated failures and a perception of unreliable service, potentially violating regulatory expectations for network stability. Professional reasoning. Professionals in this field should adopt a structured decision-making process that begins with a thorough understanding of the problem, including its immediate and potential long-term consequences. This involves a comprehensive risk assessment that considers environmental factors, regulatory requirements, and the impact on service availability. The process should prioritize solutions that are not only effective in the short term but also sustainable, compliant, and resilient in the long term. Documenting all assessments, proposed solutions, and their justifications is crucial for accountability and future reference. When faced with time constraints, it is essential to communicate the risks associated with temporary measures and to establish clear timelines for implementing permanent solutions. Question 6. Risk assessment procedures indicate that a critical mobile backhaul link is scheduled for activation within 48 hours to support a new cell site. The field engineer has received the basic site survey information, but has not yet received a fully documented and approved network design that details specific IP addressing, VLAN assignments, CO-S policies, and security configurations for the new link. What is the most professional and risk-averse approach to ensure the successful and compliant deployment of this backhaul link? Option A. Delay the physical installation and configuration until a complete, validated network design document is formally approved and provided. Option B. Proceed with the physical installation and initial configuration using assumed standard parameters, with a commitment to formalize the design documentation post-activation. Option C. Deploy the link using vendor default configurations and rely on post-deployment monitoring to identify and correct any issues. Option D. Implement the physical installation and configuration based on the engineer's best judgment of typical requirements, documenting the choices made for later review. The correct answer is B. Proceed with the physical installation and initial configuration using assumed standard parameters, with a commitment to formalize the design documentation post-activation. Explanation. Scenario analysis. This scenario presents a common challenge in mobile backhaul deployment, balancing the need for rapid service activation with the imperative to adhere to established network design and security best practices. Field engineers are often under pressure to meet service-level agreements, SLAs, and customer expectations, which can lead to temptations to bypass or expedite certain validation steps. The professional challenge lies in recognizing that while speed is important, compromising fundamental design principles or security protocols can lead to long-term operational issues, increased maintenance costs, and potential security vulnerabilities, ultimately undermining the reliability and integrity of the mobile backhaul network. The absence of a documented and validated design before deployment is a significant risk. Correct approach analysis. The correct approach emphasizes the critical importance of a fully documented and validated network design prior to any physical deployment or configuration. This aligns with best practices in network engineering and Cisco's recommended methodologies for mobile backhaul. A validated design ensures that all components, configurations, and interconnections meet the specified requirements for performance, scalability, and security. It provides a baseline for troubleshooting, future upgrades, and compliance audits. Adhering to this process demonstrates professional diligence and a commitment to building robust and maintainable infrastructure, which is essential for the reliable operation of mobile services. This approach minimizes the risk of introducing errors or vulnerabilities that could impact service quality or security. Incorrect approach is analysis. Deploying and configuring network elements based on an incomplete or unvalidated design, with the intention of formalizing it later, represents a significant professional and ethical failure. This approach bypasses essential quality assurance steps. It increases the likelihood of misconfigurations, suboptimal performance, and security gaps, which can lead to service disruptions and require costly rework. Furthermore, it deviates from established engineering principles that mandate thorough planning and validation before implementation. Proceeding with deployment based on a best guess or assumption of standard configurations without explicit design approval is also professionally unacceptable. This introduces an unacceptable level of risk, as assumptions may not hold true for the specific deployment environment or may not align with the overall network strategy. It undermines the principle of engineering rigor and can lead to inconsistent network behavior and increased troubleshooting complexity. Relying solely on vendor default configurations without a specific design review and validation is another failure. While vendor defaults can be a starting point, they are rarely optimized for a specific mobile backhaul deployment and may not incorporate necessary security hardening or performance tuning. This approach neglects the responsibility of the engineer to ensure the network is tailored to its intended purpose and meets all operational and security requirements. Professional reasoning. Field engineers must adopt a systematic and disciplined approach to network deployment. This involves prioritizing adherence to documented design specifications and validation procedures. When faced with pressure to expedite deployment, engineers should clearly communicate the risks associated with bypassing these critical steps to project management or relevant stakeholders. The decision-making process should involve 1. Understanding the project's objectives and constraints, including SLAs. 2. Identifying all applicable design documentation and validation checklists. 3. Assessing the potential impact of any deviation from the documented plan. 4. Escalating concerns or seeking clarification when ambiguities or risks are identified. 5. Prioritizing the integrity and long-term stability of the network over short-term expediency. Question 7. Consider a scenario where a field engineer is tasked with configuring a new mobile backhaul router for a critical site. The deployment ticket specifies a particular configuration, but the engineer notices that some parameters deviate from Cisco's recommended best practices for this model and the intended service type. The ticket is marked as urgent due to an impending service launch. The engineer's supervisor, under pressure to meet the launch deadline, suggests proceeding with the ticket's configuration, stating that it will likely work and can be fine-tuned later. Which of the following represents the most professionally responsible approach for the field engineer? Option A. Implement the configuration as per the ticket, but document all deviations from best practices and potential risks in a separate report to be submitted after the deployment is complete. Option B. Proceed with the configuration as specified in the ticket, prioritizing the urgent deadline and the supervisor's directive, with the understanding that adjustments can be made post-deployment. Option C. Halt the deployment and insist on a full review and correction of the configuration to align with Cisco best practices and potential regulatory requirements before proceeding, even if it delays the service launch. Option D. Implement the configuration as specified in the ticket, but proactively seek verbal confirmation from a senior engineer that the deviations are acceptable for this specific urgent scenario. The correct answer is B. Proceed with the configuration as specified in the ticket, prioritizing the urgent deadline and the supervisor's directive, with the understanding that adjustments can be made post-deployment. Explanation. Scenario analysis. This scenario presents a common challenge in mobile backhaul deployment, balancing the need for rapid service provisioning with adherence to established best practices and regulatory compliance. The pressure to meet aggressive deployment timelines can lead to shortcuts that compromise network stability, security, and long-term maintainability. Field engineers must exercise sound judgment to identify and mitigate risks associated with deviating from approved methodologies, especially when faced with conflicting priorities. The professional challenge lies in advocating for and implementing solutions that are technically sound and compliant, even when under pressure to deliver quickly. Correct approach analysis. The correct approach involves a thorough assessment of the proposed configuration against documented best practices and the specific requirements of the mobile backhaul network. This includes verifying that the configuration aligns with Cisco's recommended deployment guides for the specific hardware and software versions in use, ensuring optimal performance, security, and interoperability. It also entails confirming that the configuration adheres to any relevant local regulatory requirements for telecommunications infrastructure, even if not explicitly detailed in the immediate deployment ticket. This proactive verification process prevents potential issues down the line, reduces the likelihood of service disruptions, and ensures the network's long-term health and compliance. This aligns with the professional responsibility to deliver robust and reliable services. Incorrect approach is analysis. Implementing the configuration without verification, based solely on the ticket's instructions, is professionally unacceptable because it bypasses critical quality assurance steps. This could lead to misconfigurations that impact network performance, introduce security vulnerabilities, or violate operational standards, potentially resulting in service outages or non-compliance with regulatory mandates for network integrity. Accepting the configuration based on a verbal assurance from a senior engineer without independent verification is also professionally unsound. While collaboration is important, ultimate responsibility for the deployed configuration rests with the field engineer. Relying on verbal assurances without due diligence can perpetuate errors and does not absolve the engineer of accountability if issues arise. It also fails to establish a clear, documented record of verification, which is crucial for troubleshooting and auditing. Proposing a configuration that deviates significantly from best practices to expedite deployment, even if it appears functional in a limited test, is a risky and unprofessional approach. Such deviations can introduce unforeseen complexities, hinder future upgrades, and create security risks. The short-term gain in speed is outweighed by the long-term potential for instability and increased maintenance overhead, and it may also inadvertently violate implicit regulatory expectations for network resilience and security. Professional reasoning. Field engineers should adopt a systematic decision-making process that prioritizes verification and compliance. When presented with a deployment task, the first step is to thoroughly review the provided documentation and compare it against known best practices and relevant regulatory guidelines. If any discrepancies or potential issues are identified, the engineer should flag these for clarification and resolution before proceeding with the implementation. This involves clear communication with supervisors and relevant technical teams to ensure that all concerns are addressed. The engineer should always strive to implement solutions that are both efficient and robust, understanding that a well-executed deployment, even if it takes slightly longer, is ultimately more professional and beneficial than a rushed one that leads to future problems. Documenting all verification steps and decisions is also a critical part of professional practice. Question 8. The investigation demonstrates that a customer is experiencing intermittent connectivity issues on a mobile backhaul link, reporting that their service is not meeting the expected throughput as per their service level agreement, SLA. The field engineer arrives on site and observes that the current interface configuration is set to a lower bandwidth than the physical port's capability. The customer is requesting an immediate upgrade to the highest possible bandwidth to resolve the issue. Which of the following represents the most professional and effective approach for the field engineer to take in this situation? Option A. Implement a temporary workaround, such as adjusting quality of service, (QoS) parameters, without fully documenting the changes or verifying if it addresses the root cause of the intermittent connectivity. Option B. Verify the customer's specific SLA requirements for throughput and consult network documentation to confirm the upstream network's capacity and the feasibility of a higher bandwidth configuration before making any changes. Option C. Immediately reconfigure the interface to the highest possible bandwidth supported by the physical port to satisfy the customer's request and restore perceived performance. Option D. Inform the customer that the current configuration is the maximum supported by the equipment and that no further upgrades are possible, without investigating alternative solutions or escalating the issue. The correct answer is B. Verify the customer's specific SLA requirements for throughput and consult network documentation to confirm the upstream network's capacity and the feasibility of a higher bandwidth configuration before making any changes. Explanation. This scenario presents a common challenge in mobile backhaul deployment, ensuring service level agreement (SLA) compliance while managing network resources efficiently. The field engineer must balance the immediate need for service restoration with the long-term implications of network configuration choices. The professional challenge lies in interpreting the customer's requirements, understanding the technical capabilities and limitations of the deployed equipment, and adhering to the operational guidelines set forth by the service provider, all within the context of the 500-240 Cisco Mobile Backhaul for Field Engineers Exams implied regulatory framework, which prioritizes service delivery and network integrity. The correct approach represents best professional practice because it prioritizes a thorough understanding of the customer's SLA and the network's capabilities before implementing a solution. This ensures that the deployed configuration not only restores service, but also meets the agreed-upon performance metrics. By engaging with the customer and verifying the technical feasibility, the engineer upholds the principles of service delivery and customer satisfaction, which are implicitly governed by industry standards and contractual obligations. This proactive verification minimizes the risk of future service degradations or SLA breaches, thereby protecting the reputation of the service provider. An incorrect approach that involves immediately reconfiguring the interface to a higher bandwidth without verifying the customer's actual SLA or the upstream network's capacity is professionally unacceptable. This action could lead to network congestion or performance issues for other services, potentially violating broader network operational guidelines and impacting other customers. It demonstrates a failure to adhere to due diligence and a disregard for the interconnected nature of the backhaul network. Another incorrect approach, which is to simply inform the customer that the current configuration is the maximum supported by the equipment without exploring alternative solutions or escalating the issue, fails to meet the professional obligation of problem resolution. While technically accurate, it neglects the customer's need for service and the engineer's role in finding solutions within the operational framework. This approach can lead to customer dissatisfaction and potential loss of business, indicating a lack of proactive problem solving. A third incorrect approach, which is to implement a temporary workaround that does not fully address the underlying issue and is not documented, is also professionally unsound. Temporary fixes, if not properly managed and documented, can lead to recurring problems, network instability, and difficulties in future troubleshooting. This lack of documentation and permanent resolution violates best practices for network management and operational efficiency. The professional decision-making process for similar situations should involve a structured approach. 1. Understand the problem and the customer's stated requirements. 2. Consult relevant documentation, including SLAs, network diagrams, and equipment specifications. 3. Assess the technical feasibility of proposed solutions against network capabilities and constraints. 4. Communicate clearly with the customer regarding findings, proposed solutions, and potential impacts. 5. Implement the most appropriate solution, ensuring it aligns with operational policies and service commitments. 6. Document all actions taken and verify the resolution with the customer. 7. Escalate issues that cannot be resolved within the field engineer's scope of authority or expertise. Question 9. Upon reviewing the planned upgrade of a mobile base station's backhaul from an aging E1 microwave link to a new Ethernet fiber optic circuit, the field engineer identifies that the existing E1 link is operating at its maximum capacity. The new fiber circuit has been provisioned and tested in isolation, but the customer has expressed extreme sensitivity to any service interruption, citing critical real-time data transmission requirements. What is the most professionally responsible approach to ensure minimal to zero service disruption during the migration, adhering to UK regulatory expectations for service continuity? Option A. Proceed with the migration by performing a hard cutover during the customer's off-peak hours, accepting a brief, unavoidable service interruption. Option B. Inform the customer that a brief service interruption is unavoidable due to capacity constraints, and proceed with the cutover during the next available maintenance window. Option C. Immediately disconnect the E1 microwave link and activate the new fiber optic link during a scheduled low-traffic window, assuming the new link will perform adequately. Option D. Establish the new fiber optic link in parallel with the existing E1 microwave link, synchronize both, and gradually migrate traffic to the fiber link, ensuring continuous service throughout the process. Correct answer is D. Establish the new fiber optic link in parallel with the existing E1 microwave link, synchronize both, and gradually migrate traffic to the fiber link, ensuring continuous service throughout the process. Explanation. Scenario analysis. This scenario presents a common implementation challenge in mobile backhaul networks, ensuring service continuity and adherence to service level agreements (SLAs) during a planned network upgrade. The field engineer is tasked with migrating a critical customer's backhaul traffic from an aging E1-based microwave link to a new Ethernet-based fiber optic circuit. The challenge lies in minimizing or eliminating service disruption for the customer, who relies on this link for their mobile base station operations. The engineer must balance the need for timely upgrade completion with the imperative to maintain service availability, as any downtime could lead to significant revenue loss for the operator and reputational damage. The regulatory framework for telecommunications in the UK, as governed by Ofcom, emphasizes service reliability and consumer protection, making adherence to SLAs a critical operational requirement. Correct approach analysis. The correct approach involves meticulous planning and execution of a hitless or graceful cutover. This typically entails establishing the new fiber optic link in parallel with the existing E1 microwave link, ensuring both are fully operational and synchronized. Traffic is then gradually shifted from the old to the new link, often using technologies like Link Aggregation Control Protocol, LACP, or similar mechanisms that allow for seamless failover without service interruption. This method directly aligns with Ofcom's expectations for service providers to maintain high levels of network availability and meet contractual obligations, SLAs. It demonstrates best professional practice by prioritizing customer service continuity and minimizing business impact, thereby upholding the operator's commitment to reliable service delivery as mandated by regulatory principles. Incorrect approaches analysis. A hard cutover, where the E1 link is simply disconnected and the fiber link is immediately activated without prior parallel operation or traffic synchronization, is a significant regulatory and ethical failure. This approach risks a complete service outage, directly violating SLA terms and Ofcom's requirements for service reliability. It demonstrates a lack of professional diligence and foresight, potentially leading to penalties and customer dissatisfaction. Another incorrect approach would be to proceed with the upgrade without adequate testing of the new fiber link under load conditions, or without a robust rollback plan. This could lead to unexpected performance issues or complete failure of the new link after the cutover, again resulting in service disruption and a breach of SLAs. This failure to perform due diligence and risk mitigation is professionally unacceptable and contravenes the spirit of regulatory oversight aimed at ensuring dependable telecommunications services. Finally, attempting the cutover during peak operational hours without prior customer notification or agreement, even if a brief interruption is anticipated, is also a failure. While the intention might be to minimize the impact on the customer's business operations by avoiding their busiest periods, the lack of explicit communication and consent regarding any potential disruption is a breach of professional courtesy and potentially regulatory guidelines regarding customer communication and transparency. Professional reasoning. Professionals in this field must adopt a risk-averse, customer-centric approach. The decision-making process should prioritize service continuity above all else. This involves 1. Thorough planning, understanding the customer's criticality and the impact of any disruption. 2. Parallel operation, establishing the new service alongside the old to allow for seamless transition. 3. Incremental migration, shifting traffic gradually to identify and resolve issues before full commitment. 4. Comprehensive testing, validating the new service under various load conditions. 5. Robust rollback strategy, having a clear and tested plan to revert to the old service if issues arise. 6. Clear communication, engaging with the customer throughout the process, especially regarding any planned maintenance windows or potential impacts. Adherence to these principles ensures compliance with regulatory expectations for service reliability and demonstrates a commitment to professional excellence. Question 10. Compliance review shows that a new mobile backhaul deployment in the UK has not adequately addressed the lawful intercept requirements as mandated by the UK's Investigatory Powers Act 2016. Specifically, the implementation of data retention and access protocols for lawful interception has been overlooked during the initial rollout. Which of the following approaches best addresses this compliance gap while minimizing operational disruption and legal risk? Option A. Proceed with the current deployment, assuming that future network upgrades will address the lawful intercept requirements and inform the relevant authorities of the delay in full compliance. Option B. Immediately halt all network operations and initiate a full network redesign to incorporate the required lawful intercept features, prioritizing compliance over service continuity. Option C. Rely on existing network security features and general data protection measures, assuming they inherently satisfy the lawful intercept obligations under the Investigatory Powers Act 2016, and await further specific instructions from law enforcement. Option D. Conduct a thorough assessment of the UK's Investigatory Powers Act 2016 requirements for lawful intercept. Engage with the legal and compliance teams to define the necessary technical configurations, and implement these changes in a phased approach during scheduled maintenance windows, ensuring all configurations are documented and verified. The correct answer is B. Immediately halt all network operations and initiate a full network redesign to incorporate the required lawful intercept features, prioritizing compliance over service continuity. Explanation. Scenario analysis. This scenario presents a common implementation challenge in mobile backhaul networks, ensuring compliance with evolving regulatory requirements for lawful intercept capabilities while maintaining network performance and security. The challenge lies in balancing the technical demands of implementing these features with the legal obligations, which can be complex and vary based on the specific jurisdiction's telecommunications laws. Field engineers must possess a deep understanding of both the Cisco mobile backhaul technologies and the applicable regulatory framework to avoid service disruptions, legal penalties, and security vulnerabilities. The pressure to deploy quickly can sometimes lead to shortcuts that compromise compliance. Correct approach analysis. The correct approach involves a proactive and thorough integration of lawful intercept requirements into the network design and deployment phases. This means consulting the relevant regulatory documentation, e.g., specific directives from the relevant national telecommunications regulator, and Cisco's best practices for lawful intercept features. It necessitates understanding the specific data types and formats required for interception, the secure transmission mechanisms, and the auditing capabilities. By engaging with the legal and compliance teams early and ensuring that all deployed equipment and configurations meet these mandates, the field engineer upholds professional responsibility and ensures the network is legally compliant from inception. This approach minimizes the risk of costly remediation and legal repercussions. Incorrect approaches analysis. Implementing lawful intercept features only after a regulatory audit or a specific request from law enforcement is a reactive and professionally unsound approach. This failure to integrate compliance from the outset creates significant risks. It can lead to delays in fulfilling legal obligations, potential fines, and reputational damage. Furthermore, retrofitting such capabilities can be technically complex and may require extensive network reconfigurations, potentially impacting service availability. Assuming that standard network security measures are sufficient to meet lawful intercept requirements is another critical failure. Lawful intercept mandates often specify particular protocols, data access methods, and reporting mechanisms that go beyond general security practices. Relying on assumptions without verifying against specific regulatory requirements is a direct violation of professional duty and legal obligations. Deploying lawful intercept features without proper documentation and verification of their operational status and adherence to regulatory specifications is also unacceptable. This lack of diligence means there is no assurance that the implemented features are functioning as required by law, leaving the organization vulnerable to non-compliance. It demonstrates a disregard for the meticulous nature of regulatory adherence. Professional reasoning. Field engineers must adopt a risk-based, compliance-first mindset. When faced with implementation challenges, the professional decision-making process should involve 1. Identifying all applicable regulatory requirements for the specific jurisdiction. 2. Consulting official documentation and seeking clarification from legal/compliance departments when necessary. 3. Integrating compliance requirements into the initial design and planning phases. 4. Verifying that all deployed hardware and software configurations meet these requirements. 5. Documenting all implementation steps and verification procedures thoroughly. 6. Conducting regular audits and testing to ensure ongoing compliance. This systematic approach ensures that technical deployments align with legal and ethical obligations, safeguarding both the organization and the engineer's professional integrity. Question 11. Examination of the data shows that a planned upgrade of the mobile backhaul network infrastructure is required to support increased data traffic and introduce new services. The current infrastructure is aging and becoming increasingly difficult to maintain. The primary concern is to minimize any disruption to existing mobile services during the upgrade process. What is the most professionally responsible approach to implementing this backhaul network upgrade? Option A. Postpone the upgrade indefinitely, citing the complexity of the migration and the potential for service disruption, and focus on optimizing the current infrastructure. Option B. Implement a phased migration strategy, where new equipment is installed and tested in parallel with the existing infrastructure. Services are gradually migrated to the new system after successful validation, with a clear rollback plan in place. Option C. Conduct the upgrade during the busiest network traffic hours to minimize the overall perceived downtime for users, accepting a higher risk of performance degradation during the transition. Option D. Execute a complete rip and replace of all existing backhaul equipment with new hardware, performing the cutover during a scheduled maintenance window, assuming minimal impact due to the short duration of the outage. The correct answer is B. Implement a phased migration strategy, where new equipment is installed and tested in parallel with the existing infrastructure. Services are gradually migrated to the new system after successful validation, with a clear rollback plan in place. Explanation. The scenario presents a common implementation challenge in mobile backhaul networks, ensuring service continuity and adherence to service-level agreements, SLAs, during a planned network upgrade. The professional challenge lies in balancing the need for modernization with the imperative to minimize disruption to existing services, which directly impacts customer satisfaction and potential contractual penalties. Careful judgment is required to select an upgrade strategy that is both technically sound and operationally responsible. The correct approach represents best professional practice because it prioritizes a phased, controlled migration. This strategy allows for thorough testing and validation at each stage, significantly reducing the risk of widespread service outages. By maintaining the existing infrastructure in parallel until the new system is fully operational and verified, it provides a fallback mechanism, ensuring that if any issues arise during the transition, services can be quickly reverted. This aligns with the professional obligation to deliver reliable services and uphold contractual commitments, which are implicitly governed by industry best practices and customer agreements that emphasize uptime and performance. While specific regulations for mobile backhaul in the context of the 500-240 exam are not explicitly detailed as a separate jurisdiction, the underlying principles of network reliability and service delivery are universally expected and form the basis of professional conduct in telecommunications. An incorrect approach that involves a rip and replace method without adequate pre-migration testing or a rollback plan is professionally unacceptable. This strategy carries a high risk of immediate and extensive service disruption. Such a failure to ensure service continuity would violate the implicit professional duty to maintain network stability and could lead to breaches of SLAs, resulting in financial penalties and reputational damage. Ethically, it demonstrates a disregard for the impact on end users and the business operations that depend on the mobile backhaul service. Another incorrect approach, which is to postpone the upgrade indefinitely due to perceived complexity, is also professionally deficient. While risk mitigation is important, stagnation in network infrastructure leads to obsolescence, reduced performance, and increased vulnerability to security threats. This inaction fails to meet the professional responsibility to evolve and maintain a competitive and secure network, potentially impacting the operator's ability to offer new services or meet future demand. A third incorrect approach, which is to implement the upgrade during peak traffic hours to minimize the perceived downtime window, is a flawed strategy. While the intention might be to reduce the duration of potential impact, performing critical infrastructure changes during periods of high network utilization dramatically increases the risk of cascading failures and performance degradation. This is because any unforeseen issue, however minor, will have a magnified impact on a larger number of users and services. This approach prioritizes a potentially shorter but riskier window over a more controlled, albeit potentially longer, transition. The professional decision-making process for similar situations should involve a comprehensive risk assessment, detailed planning, stakeholder communication, and a phased implementation strategy with robust rollback capabilities. Prioritizing service continuity and adherence to SLAs should be the guiding principles, supported by thorough testing and validation at every step of the upgrade process. Question 12. Performance analysis shows that a critical mobile backhaul link is experiencing intermittent packet loss, impacting voice quality for a significant number of subscribers. The planned network upgrade involves replacing the aging optical transport equipment on this link with newer, higher-capacity devices. The upgrade is scheduled for a low-traffic window, but the risk of extended downtime during the transition is a concern. What is the most professional and regulatory compliant approach to manage this upgrade while minimizing subscriber impact? Option A. Proceed with the upgrade by replacing the equipment directly without extensive pre-deployment testing or a documented rollback plan to expedite the process and minimize the scheduled downtime. Option B. Implement a phased migration strategy, utilizing the existing infrastructure to establish temporary redundant paths or an overlay network to maintain service continuity for subscribers while the new equipment is installed and tested. Option C. Immediately proceed with a full rip and replace of all existing optical transport equipment on the link during the scheduled maintenance window, assuming the new equipment will resolve the packet loss issue. Option D. Defer the upgrade until the intermittent packet loss issue on the current link is fully resolved, as upgrading a faulty link could exacerbate existing problems. The correct answer is B. Implement a phased migration strategy, utilizing the existing infrastructure to establish temporary redundant paths or an overlay network to maintain service continuity for subscribers while the new equipment is installed and tested. Explanation. Scenario analysis. This scenario presents a common implementation challenge in mobile backhaul networks, ensuring service continuity and meeting stringent service level agreements, SLAs, during a planned network upgrade. The challenge lies in balancing the need for modernization with the critical requirement of minimizing service disruption for existing customers. Field engineers must possess a deep understanding of the network's current state, the proposed upgrade's impact, and the relevant regulatory framework governing service provision and network resilience. The pressure to complete the upgrade efficiently while adhering to these constraints makes professional judgment paramount. Correct approach analysis. The correct approach involves a phased migration strategy, leveraging the capabilities of the existing infrastructure to support the new services during the transition. This aligns with the principles of network resilience and service continuity, which are often implicitly or explicitly mandated by regulatory bodies to ensure reliable telecommunications services. By establishing a temporary overlay network or utilizing existing redundant paths, the engineer can migrate services incrementally. This minimizes the risk of a widespread outage and allows for thorough testing of new components before fully decommissioning old ones. This method demonstrates adherence to best practices in network engineering, prioritizing customer impact and service stability, which are key considerations in regulatory compliance for telecommunications providers. Incorrect approach is analysis, a rip and replace approach, where all existing equipment is removed and replaced simultaneously without a robust rollback plan or interim service support, represents a significant regulatory and ethical failure. This method drastically increases the risk of prolonged service outages, violating the implicit and often explicit regulatory obligations to provide reliable service. It also demonstrates a lack of professional due diligence in assessing and mitigating potential customer impact. Another incorrect approach is to proceed with the upgrade without adequately testing the new equipment in a lab environment or a controlled pilot. This disregards the principle of ensuring network integrity and service quality before deployment. Regulatory bodies expect telecommunications providers to exercise due care in deploying new technologies to prevent service degradation or failure. This approach risks introducing unforeseen issues that could lead to widespread service disruption, a direct contravention of service reliability expectations. Furthermore, neglecting to document the migration process thoroughly, including rollback procedures and contingency plans, is professionally unsound and can have regulatory implications. In the event of an incident, a lack of documentation hinders rapid troubleshooting and recovery, potentially prolonging outages and making it difficult to demonstrate compliance with incident reporting requirements. Professional reasoning. Field engineers facing such implementation challenges should adopt a structured decision-making process. This begins with a comprehensive understanding of the project's objectives, the existing network's architecture, and the specific requirements of the upgrade. Crucially, this must be followed by a thorough risk assessment, identifying potential points of failure and their impact on service continuity. The engineer should then consult relevant network design documents, vendor specifications, and, importantly, any applicable regulatory guidelines or industry best practices related to network upgrades and service provision. Developing a detailed migration plan that includes phased implementation, testing protocols, rollback strategies, and clear communication channels is essential. Prioritizing customer impact and service stability throughout the planning and execution phases ensures that the upgrade is not only technically successful, but also professionally responsible and compliant. Question 13. The audit findings indicate a pattern of intermittent connectivity issues on a critical mobile backhaul link that have been repeatedly addressed with quick fixes. As a field engineer tasked with resolving this ongoing problem, what is the most appropriate course of action to ensure long-term network stability and compliance with operational standards? Option A. Apply a standard troubleshooting script for intermittent faults, focusing on re-establishing a stable link without necessarily pinpointing the exact cause of the initial disruption. Option B. Conduct a comprehensive root cause analysis, including detailed log review, performance metric correlation, and configuration validation against established network design principles to identify and permanently resolve the underlying issue. Option C. Immediately implement a series of common configuration adjustments known to resolve similar connectivity problems, prioritizing service restoration over in-depth investigation. Option D. Document the recent fixes and recommend monitoring the link closely for a period, assuming the intermittent nature will resolve itself with continued observation. The correct answer is B. Conduct a comprehensive root cause analysis, including detailed log review, performance metric correlation, and configuration validation against established network design principles, to identify and permanently resolve the underlying issue. Explanation. Scenario analysis. This scenario presents a professional challenge due to the inherent conflict between immediate operational needs and the long-term integrity of the mobile backhaul network, as mandated by regulatory frameworks. Field engineers are often under pressure to restore service quickly, which can lead to shortcuts. However, The audit findings highlight a systemic issue that, if not addressed properly, could result in non-compliance with service level agreements, SLAs, and potentially impact public safety or critical communications, depending on the specific services supported by the backhaul. The challenge lies in balancing the urgency of service restoration with the requirement for thorough, documented, and compliant procedures. Correct approach analysis. The correct approach involves a systematic investigation that prioritizes identifying the root cause of the intermittent connectivity. This aligns with the principles of good engineering practice and regulatory compliance, which emphasize proactive problem-solving and robust network management. By performing detailed diagnostics, analyzing logs, and verifying configuration against established standards, the engineer ensures that the fix is not merely a temporary patch but a permanent resolution. This methodical approach prevents recurrence, maintains network stability, and demonstrates due diligence in adhering to operational guidelines and potentially any specific service assurance requirements stipulated by regulatory bodies governing telecommunications infrastructure. This also ensures that any changes made are properly documented, which is a common regulatory requirement for network modifications. Incorrect approaches analysis. Implementing a configuration change without a thorough root cause analysis is a significant regulatory and ethical failure. It risks masking the underlying problem, leading to intermittent issues that could violate service-level agreements, SLAs, and potentially impact critical services. This approach demonstrates a lack of due diligence and a failure to adhere to best practices for network troubleshooting and maintenance, which are often implicitly or explicitly required by telecommunications regulations. Applying a generic troubleshooting script without verifying its relevance to the specific symptoms is also professionally unacceptable. This can lead to wasted time, incorrect diagnosis, and a failure to address the actual issue. It bypasses the critical thinking required for effective problem solving and can result in a non-compliant network state if the underlying problem is not resolved. This reflects a failure to apply engineering expertise and adhere to operational procedures designed to ensure network reliability. Ignoring the intermittent nature of the fault and focusing solely on restoring a stable connection without understanding the cause is a short-sighted approach. While it might provide temporary relief, it fails to address the systemic issue. This can lead to repeated failures, impacting service quality and potentially violating regulatory obligations related to network availability and performance. It demonstrates a lack of commitment to long-term network health and compliance. Professional reasoning. In situations involving intermittent network faults, a professional field engineer should adopt a structured problem-solving methodology. This begins with a clear understanding of the reported symptoms and their potential impact. The next step is to gather all available data, including logs, performance metrics, and configuration details. Based on this data, a hypothesis about the root cause should be formed. The engineer should then devise and execute a plan to test this hypothesis, which may involve specific diagnostic tools or controlled configuration changes. Crucially, any changes made must be documented and their impact verified. If the initial hypothesis is incorrect, the process should be repeated with a revised hypothesis. This iterative, data-driven approach ensures that the problem is not only resolved but also understood, preventing future occurrences and maintaining compliance with operational and regulatory standards. Question 14. Analysis of an implementation challenge for a planned upgrade of a Cisco mobile backhaul network, where a field engineer must decide on the most appropriate strategy to minimize service disruption to existing 4G and 5G subscribers during the transition to new aggregation switches. The engineer has identified several potential approaches, each with varying levels of risk and complexity. Option A. Proceed with the upgrade by replacing equipment on a site-by-site basis during peak traffic hours, relying solely on vendor-provided installation guides without pre-deployment testing. Option B. Immediately deploy the new aggregation switches across all sites simultaneously during business hours to expedite the upgrade process. Option C. Implement the upgrade by performing a full network cutover during a scheduled maintenance window, but without a documented rollback procedure in case of unforeseen issues. Option D. Conduct a comprehensive lab simulation of the upgrade, followed by a phased rollout starting with a pilot deployment in a low-traffic area, and then a scheduled cutover during a low-usage period with a defined rollback plan. The correct answer is D. Conduct a comprehensive lab simulation of the upgrade, followed by a phased rollout starting with a pilot deployment in a low-traffic area, and then a scheduled cutover during a low-usage period with a defined rollback plan. Explanation: this scenario presents a common implementation challenge in mobile backhaul, ensuring service continuity during a planned network upgrade. Professional challenge lies in balancing the need for modernization with the critical requirement of minimizing disruption to existing mobile services, which directly impacts customer experience and revenue. Field engineers must possess a deep understanding of the network architecture, the upgrade process, and the potential impact on service level agreements, SLAs. Careful judgment is required to select an implementation strategy that mitigates risks effectively. The correct approach represents best professional practice because it prioritizes a phased, controlled migration. This involves thorough pre-deployment testing in a lab environment to validate the new equipment and configuration against the existing network. Following this, a pilot deployment in a non-critical or low-traffic area allows for real-world validation without jeopardizing core services. The final stage involves a carefully scheduled cutover during a low-usage window, with robust rollback procedures in place. This methodical approach aligns with industry best practices for network upgrades, emphasizing risk reduction and service assurance. While specific regulations for mobile backhaul field engineers in the context of the 500-240 exam are not explicitly detailed as separate legal documents, the underlying principles of responsible engineering, adherence to vendor best practices, and ensuring service reliability are implicitly governed by the professional standards expected of Cisco certified engineers. These standards mandate a duty of care to the network and its users, preventing service degradation. An incorrect approach that involves immediate, full-scale deployment without prior testing or a pilot phase represents a significant regulatory and ethical failure. This demonstrates a disregard for the potential impact on service availability, which could lead to breaches of SLAs and customer dissatisfaction. Such an approach also fails to adhere to the principles of diligent engineering and risk management expected of a field engineer. Another incorrect approach, such as relying solely on vendor documentation without independent validation or a rollback plan, is also professionally unacceptable. This shows a lack of proactive problem-solving and an over-reliance on external guidance without ensuring it is suitable for the specific deployment environment. This can lead to unforeseen issues that are difficult to resolve quickly, impacting service. A third incorrect approach, performing the upgrade during peak traffic hours without adequate preparation, directly contravenes the principle of minimizing service disruption and demonstrates poor planning and execution, potentially leading to widespread service outages and significant financial and reputational damage. The professional reasoning process for similar situations should involve a structured risk assessment. This begins with understanding the scope and impact of the proposed change. Next, evaluate different implementation strategies, considering their associated risks and benefits. Prioritize strategies that offer the highest degree of service assurance and the lowest risk of disruption. Always incorporate thorough testing, pilot deployments, and comprehensive rollback plans. Finally, ensure clear communication with all stakeholders, including management and operations teams, regarding the planned upgrade and potential impacts. Question 15. Process analysis reveals that a field engineer, during an urgent service restoration on a critical mobile backhaul link, identifies a configuration parameter that, if adjusted to a non-standard value, would immediately restore service. However, this adjustment deviates from the approved network design documentation and may not fully comply with specific technical standards outlined in the regulatory framework governing mobile backhaul operations. The engineer is under significant pressure to restore service quickly. What is the most appropriate course of action for the field engineer in this situation? Option A. Inform the Network Operations Center of the situation. Propose the non-standard configuration change and await formal approval before implementing it, even if it delays service restoration. Option B. Proceed with the non-standard configuration change without any documentation or seeking approval, relying on the immediate restoration of service as justification. Option C. Implement the non-standard configuration change to restore service immediately, documenting the deviation and initiating the formal approval process concurrently with the restoration. Option D. Implement the non-standard configuration change to restore service immediately and then document the deviation and seek formal approval retrospectively. The correct answer is D. Implement the non-standard configuration change to restore service immediately, and then document the deviation and seek formal approval retrospectively. Explanation. Scenario analysis. This scenario presents a common ethical dilemma in field engineering, where a perceived shortcut could lead to immediate operational gains, but carries significant risks of non-compliance and potential future network instability. The challenge lies in balancing the pressure for rapid deployment and service restoration, with the imperative to adhere to established network design principles and regulatory guidelines. A field engineer must exercise sound judgment, prioritizing long-term network integrity and compliance over short-term expediency. Correct approach analysis. The correct approach involves meticulously documenting the deviation, obtaining formal approval from the relevant network design authority, and ensuring that the proposed solution meets all applicable regulatory requirements and internal standards. This upholds professional integrity by demonstrating a commitment to responsible engineering practices. It ensures that any deviation is understood, assessed for risk, and formally sanctioned, thereby maintaining accountability and transparency. This aligns with the ethical obligation to provide services in a manner that is safe, reliable, and compliant with all governing frameworks, preventing potential future issues and ensuring the integrity of the mobile backhaul network. Incorrect approaches analysis. One incorrect approach involves implementing the change without proper documentation or approval, relying solely on the engineer's judgment. This is a direct violation of professional ethics and likely regulatory guidelines that mandate traceable changes and adherence to approved designs. It bypasses critical review processes designed to identify potential risks and ensure compliance, leading to an undocumented and potentially non-compliant network configuration. Another incorrect approach is to proceed with the change after only informal consultation with a peer, without formal approval or documentation. While consultation is valuable, it does not substitute for the formal change management and approval processes required by most regulatory bodies and internal policies. This approach creates ambiguity regarding responsibility and accountability for the deviation, and it fails to ensure that the change has been vetted against all necessary technical and regulatory standards. A third incorrect approach is to implement the change and then attempt to retroactively document it without prior approval. This is ethically unsound as it implies a deliberate attempt to circumvent established procedures. It also carries the risk that the deviation may have already caused issues or been flagged by monitoring systems, and the retroactive documentation may not accurately reflect the situation or satisfy regulatory scrutiny. Professional reasoning. Professionals should employ a structured decision-making process that prioritizes adherence to established protocols and regulatory frameworks. When faced with a situation requiring a deviation from standard practice, the engineer should 1. Identify the deviation and its potential impact. 2. Consult relevant documentation, standards, and regulations. 3. If a deviation is necessary, follow the formal change management process, which typically involves proposing the change, documenting the rationale and impact, seeking approval from appropriate authorities, and ensuring all regulatory requirements are met. 4. If immediate action is critical and formal approval is delayed, clearly document the emergency action taken and the rationale, and expedite the formal approval process. This systematic approach ensures that decisions are well-informed, accountable, and compliant, safeguarding both the network and the engineer's professional standing. Question 16. Benchmark analysis indicates that a critical mobile backhaul link is experiencing intermittent packet loss. During your investigation, you identify a recent configuration change implemented by a vendor partner, intended to optimize a different service, which appears to be directly correlated with the onset of the packet loss. You are required to submit a report detailing the findings and proposed remediation. How should you proceed to ensure the integrity of your report and maintain professional relationships? Option A. Document the packet loss and clearly state that the vendor's recent configuration change is the identified cause, providing specific technical details of its impact. Option B. Attribute the packet loss to general network congestion without mentioning the vendor's configuration change, to avoid potential conflict. Option C. Conclude that the packet loss is an inherent, unresolvable characteristic of the link, without further investigation into specific contributing factors. Option D. Omit the finding about the vendor's configuration change from the report to prevent any negative repercussions for the vendor. Correct answer is A. Document the packet loss and clearly state that the vendor's recent configuration change is the identified cause, providing specific technical details of its impact. Explanation. Scenario analysis. This scenario presents a professional challenge rooted in the ethical obligation to maintain the integrity of network performance data and the potential for perceived bias. A field engineer is tasked with troubleshooting a mobile backhaul link that is experiencing intermittent packet loss. During the investigation, the engineer discovers that a configuration change made by a vendor partner, intended to improve a different aspect of service, is inadvertently contributing to the packet loss. The challenge lies in how to report this finding. Directly attributing the issue to the vendor's change could strain the relationship and potentially lead to disputes, impacting future collaboration. However, withholding or downplaying this information would compromise the accuracy of the network performance report and could lead to incorrect long-term remediation strategies, ultimately affecting service quality for end users. The engineer must balance the need for accurate reporting with maintaining professional relationships. Correct approach analysis. The correct approach involves transparently and factually documenting the observed packet loss, identifying the specific configuration change that correlates with the issue, and clearly stating its impact on the backhaul link's performance. This aligns with professional engineering ethics, which mandate honesty, accuracy, and a commitment to providing reliable services. In the context of Cisco Mobile Backhaul for field engineers, this means adhering to best practices for network troubleshooting and reporting, which prioritize data-driven conclusions. The engineer's responsibility is to the network's integrity and the end user's experience, not to protect a vendor's reputation at the expense of accurate reporting. This approach fosters trust and allows for collaborative problem-solving with the vendor, based on objective evidence. Incorrect approaches analysis. One incorrect approach is to attribute the packet loss to general network congestion without specifically mentioning the vendor's configuration change. This is ethically problematic because it misrepresents the root cause, potentially leading to ineffective solutions and continued service degradation. It violates the principle of honesty in reporting and can be seen as an attempt to avoid conflict by obscuring the truth. Another incorrect approach is to omit the finding about the vendor's configuration change entirely from the report. This is a serious ethical lapse, as it constitutes withholding critical information that directly impacts the understanding of the network's performance. It undermines the purpose of the benchmark analysis and the field engineer's role in providing accurate assessments. This failure to report accurately can have long-term consequences for network planning and maintenance. A third incorrect approach is to suggest that the packet loss is an inherent characteristic of the link that cannot be resolved, without investigating potential causes or attributing it to a specific change. This demonstrates a lack of due diligence and a failure to apply proper troubleshooting methodologies. It is professionally irresponsible to conclude an issue is unresolvable without a thorough and honest investigation, especially when a specific contributing factor has been identified. Professional reasoning. Professionals in field engineering must adopt a systematic decision-making process when faced with such dilemmas. This process begins with a thorough and objective investigation to gather all relevant data. Next, the engineer should analyze the data to identify the root cause, irrespective of who or what is responsible. The findings should then be documented factually and transparently, adhering to established reporting standards. Communication is key. The engineer should present the findings to relevant stakeholders, including the vendor, in a professional and constructive manner, focusing on collaborative resolution. This approach prioritizes technical accuracy, ethical conduct, and the ultimate goal of ensuring reliable network performance. Question 17. Research into the operational integrity of a newly deployed mobile backhaul link reveals intermittent packet loss exceeding acceptable thresholds, a condition not reported by the customer. The customer, eager to activate a new service, requests a configuration change that, if implemented without addressing the packet loss, might mask the issue temporarily but could impact overall network stability. As a field engineer, what is the most ethically and professionally sound course of action? Option A. Implement the customer's requested configuration change immediately to satisfy their request and address the packet loss issue at a later, less urgent time. Option B. Adjust the performance monitoring thresholds to exclude the observed packet loss, thereby meeting the customer's immediate request and avoiding further investigation. Option C. Document the observed packet loss, inform the customer of the anomaly and its potential impact, and recommend a thorough diagnostic investigation before proceeding with any configuration changes. Option D. Proceed with the configuration change, assuming the packet loss is a transient issue unrelated to the new service activation. The correct answer is C. Document the observed packet loss, inform the customer of the anomaly and its potential impact, and recommend a thorough diagnostic investigation before proceeding with any configuration changes. Explanation. This scenario presents an ethical dilemma common in field engineering, specifically concerning the integrity of network performance data and potential conflicts of interest. The challenge lies in balancing the immediate pressure to resolve a customer issue with the long-term implications of manipulating data, which can undermine trust and lead to incorrect network design or troubleshooting decisions. The correct approach involves transparently reporting the observed anomaly and working within established protocols to diagnose the root cause, even if it means acknowledging a potential flaw in the deployed equipment or configuration. This upholds professional integrity, adheres to the principles of accurate data collection and reporting mandated by industry best practices and potentially by service-level agreements, SLAs, which rely on verifiable performance metrics. It fosters a culture of accountability and allows for genuine problem-solving, ultimately benefiting the customer and the service provider. An incorrect approach would be to artificially adjust the performance metrics to mask the anomaly. This constitutes data falsification, a serious ethical breach. It violates the principle of honesty and integrity in professional conduct. From a regulatory perspective, depending on the specific context of the mobile backhaul service, e.g., if it's part of a regulated telecommunications infrastructure, such falsification could be considered misrepresentation of service quality, potentially leading to contractual disputes or even regulatory penalties if SLAs are tied to verifiable performance. It also prevents the identification and resolution of the underlying technical issue, leading to recurring problems and customer dissatisfaction. Another incorrect approach would be to ignore the anomaly and proceed with the customer's requested configuration change without proper investigation. This demonstrates a lack of diligence and a failure to adhere to professional standards of care. It prioritizes expediency over thoroughness and could lead to a degraded network experience for other users or exacerbate the existing problem. Ethically, it represents a dereliction of duty to ensure network stability and optimal performance. The professional decision-making process in such situations should involve 1. Recognizing the ethical implications of the observed data and the customer's request. 2. Prioritizing data integrity and accurate reporting above immediate convenience. 3. Consulting relevant documentation, internal procedures, and potentially senior colleagues or management if unsure. 4. Communicating findings and proposed actions transparently to the customer, explaining the rationale behind any recommended diagnostic steps. 5. Documenting all observations, actions taken, and communications thoroughly. Question 18. The efficiency study reveals that a proposed configuration change for a mobile backhaul link could significantly reduce operational costs by utilizing a less robust, but cheaper, transmission medium. However, this change deviates from the current, proven design that ensures optimal latency and resilience, and the field engineer suspects it may negatively impact service quality under certain load conditions, potentially contravening implicit service delivery standards. The engineer is under pressure to meet cost-saving targets. What is the most professionally responsible course of action for the field engineer? Option A. Implement the proposed cost-saving configuration change immediately to meet the efficiency targets, assuming the risk of minor service degradation is acceptable. Option B. Proceed with the original, more expensive configuration without implementing the proposed change, citing potential risks without further investigation or discussion. Option C. Escalate concerns about potential service quality impact to network planning and operations management, requesting a thorough impact assessment and expert consultation before any changes are made. Option D. Implement the proposed configuration change, but document it as an experimental trial, without seeking formal approval or expert validation. The correct answer is A. Implement the proposed cost-saving configuration change immediately to meet the efficiency targets, assuming the risk of minor service degradation is acceptable. Explanation. Scenario analysis. This scenario presents a conflict between immediate cost savings and long-term network integrity, a common ethical dilemma in field engineering. The pressure to meet efficiency targets can lead to shortcuts that compromise service quality and potentially violate regulatory compliance regarding network performance and reliability. The field engineer must balance the directives of their management with their professional responsibility to uphold standards. Correct approach analysis. The correct approach prioritizes adherence to established network design principles and regulatory guidelines over short-term cost reduction. This aligns with the Cisco mobile backhaul for field engineers' responsibility to ensure robust and compliant network infrastructure. Specifically, it upholds the spirit of regulations that mandate reliable service delivery and network stability, even if not explicitly detailed in the exam's jurisdiction. By escalating the concern and seeking expert consultation, the engineer demonstrates professional integrity and a commitment to best practices, preventing potential future failures and associated regulatory scrutiny. This proactive stance ensures that any deviations from standard practice are thoroughly vetted and approved by appropriate technical authorities. Incorrect approaches analysis. One incorrect approach involves implementing the proposed changes without further investigation. This is ethically problematic as it bypasses due diligence and potentially introduces instability into the network, risking service disruption. This could lead to violations of service-level agreements, SLAs, and potentially broader regulatory noncompliance if network performance degrades below mandated thresholds. Another incorrect approach is to ignore the efficiency study's recommendations entirely and proceed with the original, more expensive configuration. While seemingly safe, this fails to engage constructively with management's objectives and misses an opportunity to explore legitimate, albeit potentially more complex, cost-saving measures that do not compromise network integrity. This can be seen as a lack of professional initiative and an unwillingness to adapt to evolving operational requirements. A third incorrect approach is to implement the changes and hope for the best, without documenting the decision or seeking validation. This is a severe ethical lapse, as it demonstrates a disregard for accountability and transparency. If network issues arise, the engineer would be unable to justify their actions, potentially facing disciplinary measures and contributing to a culture of poor engineering practice. This also undermines any future audits or troubleshooting efforts. Professional reasoning. Field engineers must develop a framework for decision-making that balances operational efficiency with technical integrity and ethical responsibility. This involves 1. Understanding the implications of any proposed change on network performance, reliability, and compliance. 2. Evaluating proposed solutions against established best practices and relevant technical standards. 3. Communicating concerns and seeking clarification or alternative solutions when faced with potentially compromising directives. 4. Documenting all decisions and actions. 5. Escalating issues to appropriate technical or management levels when consensus cannot be reached or when significant risks are identified. Question 19. The assessment process reveals that a field engineer, during the final stages of a mobile backhaul network deployment, has identified a potential security vulnerability in a critical component that could expose sensitive customer data if exploited. The engineer is aware that reporting this issue now will likely cause significant delays and incur additional costs, potentially impacting project deadlines and team performance metrics. What is the most appropriate course of action for the field engineer? Option A. Immediately report the discovered vulnerability to the project manager and the designated security team, following established company protocols for incident reporting, to allow for proper assessment and remediation before network activation. Option B. Continue with the network activation as planned, hoping the vulnerability will not be exploited or will be addressed in a later maintenance cycle. Option C. Attempt to discreetly fix the vulnerability independently to avoid project delays, documenting the fix only if successful. Option D. Inform the client directly about the discovered vulnerability and the potential delays it may cause to the deployment schedule. The correct answer is A. Immediately report the discovered vulnerability to the project manager and the designated security team, following established company protocols for incident reporting, to allow for proper assessment and remediation before network activation. Explanation. Scenario analysis. This scenario presents an ethical dilemma concerning data privacy and network security within the context of mobile backhaul deployment. The field engineer has discovered a potential vulnerability that, if exploited, could compromise customer data and disrupt service. The challenge lies in balancing the immediate need to address the security flaw with the established project timelines and the potential repercussions of reporting a significant issue late in the deployment phase. The engineer must navigate potential pressure to overlook or downplay the finding to avoid delays and associated costs, while upholding professional integrity and regulatory compliance. Correct approach analysis. The correct approach involves immediately and transparently reporting the discovered vulnerability to the appropriate internal stakeholders, such as the project manager and the security team, following established company protocols. This aligns with the ethical obligation to act with integrity and competence, prioritizing the security and privacy of customer data. Cisco's own ethical guidelines and the general principles of professional engineering demand that potential risks be identified and mitigated. In the context of mobile backhaul, which carries sensitive telecommunications traffic, such a proactive stance is crucial for maintaining trust and compliance with data protection regulations. This approach ensures that the issue can be properly assessed, a remediation plan developed, and implemented before the network goes live, thereby preventing potential breaches and service disruption. Incorrect approach is analysis. Attempting to fix the vulnerability independently without proper authorization or documentation is a significant ethical and regulatory failure. It bypasses established security protocols, potentially introducing new risks or failing to address the root cause effectively. This action could violate company policy regarding unauthorized system modifications and could lead to further security incidents if the fix is inadequate. Delaying the report until after the network is operational or hoping the issue resolves itself constitutes a severe breach of professional responsibility. This inaction directly endangers customer data and service availability, exposing the company to significant legal and financial liabilities under data protection laws. It demonstrates a lack of due diligence and a disregard for the potential harm to end users. Reporting the issue to external parties or the client directly before internal reporting and resolution is also an inappropriate approach. This action undermines internal communication channels, potentially creates panic, and violates confidentiality agreements. It bypasses the established chain of command and the company's established incident response procedures, leading to disorganization and potential reputational damage. Professional reasoning. Professionals in mobile backhaul engineering must adopt a proactive and transparent approach to security. When a potential vulnerability is identified, the decision-making process should involve 1. Immediate identification and documentation of the issue. 2. Adherence to company policy for reporting security incidents. 3. Clear and timely communication with relevant internal teams, e.g., project management, security, engineering leads. 4. Collaboration on risk assessment and remediation planning. 5. Ensuring all actions are documented and authorized. This systematic approach ensures that ethical obligations and regulatory requirements are met, while also safeguarding the integrity and security of the network and customer data. Question 20. Which approach would be most appropriate for a field engineer who discovers a potential security vulnerability in a Cisco mobile backhaul device during a routine maintenance check and suspects it might have been overlooked during a previous installation? Option A. Attempt to fix the vulnerability discreetly without reporting it, to avoid causing alarm or potential issues with the previous installation team. Option B. Document the vulnerability with detailed findings and immediately report it through the company's established incident reporting channels, following all defined protocols for security issues. Option C. Inform the previous installation team directly about the suspected oversight before reporting it through official channels. Option D. Ignore the vulnerability, assuming it is minor and unlikely to be exploited, to avoid the administrative burden of reporting. Correct answer is B. Document the vulnerability with detailed findings and immediately report it through the company's established incident reporting channels, following all defined protocols for security issues. Explanation. This scenario presents a common ethical dilemma in field engineering, where a technician discovers a potential security vulnerability during routine maintenance. The challenge lies in balancing the immediate need to resolve the issue with the established protocols for reporting and remediation, especially when the discovery might reflect poorly on previous work or the vendor. The correct approach prioritizes security and compliance. By immediately documenting the vulnerability and reporting it through the designated channels, the field engineer upholds the integrity of the network and adheres to best practices for incident response. This aligns with general cybersecurity principles and the implicit expectation of responsible disclosure within the telecommunications industry, which often involves strict security policies and audit trails. This proactive reporting ensures that the vulnerability can be assessed and addressed by the appropriate teams, preventing potential exploitation and maintaining the overall security posture of the mobile backhaul network. An incorrect approach would be to ignore or downplay the vulnerability to avoid potential repercussions or extra work. This failure to report a known security flaw is a direct violation of professional responsibility and could lead to significant network compromise, data breaches, and reputational damage for both the engineer and the service provider. Such an action would also likely contravene internal company policies regarding security incident reporting and could have legal implications if a breach occurs as a result. Another incorrect approach would be to attempt to fix the vulnerability without proper authorization or documentation. While seemingly proactive, this bypasses established security procedures, potentially introducing new issues or failing to address the root cause effectively. It also undermines the audit trail and the structured incident response process, making it difficult to track, verify, and learn from the event. This can lead to a false sense of security and hinder long-term network resilience. The professional decision-making process in such situations should involve a clear understanding of company policies and ethical obligations. When a potential security issue is identified, the engineer should 1. Document the finding thoroughly and objectively. 2. Immediately report the finding through the official incident reporting mechanism. 3. Follow the guidance provided by the incident response team. 4. Avoid making unauthorized changes or disclosures. This structured approach ensures accountability, facilitates effective remediation, and upholds professional integrity.